Hi, my name is Ashish Surana, and today I'm going to talk about my final project for computer architecture class. I created a 16-bit computer with barrel shifter as a special feature. I also sneaked in few nice things, as we will see in a few minutes. I started with designing the instruction set and wrote an operation manual for it. I added shift right logical and shift left logical as special features of my instruction set. My instruction set is 2-register MIPS-like load store architecture. I reserved first 4 bits of each instruction for opcode. Remaining 12 bits are used for register numbers, immediate values, or ALU function code. For example, here is what the SLL instruction look like. And here is my complete set of instructions. Once I was satisfied with my instruction set, I moved on to writing a 2-pass assembler. I used Java for writing assembler, since it is high-level language and allows me to write good quality code with least amount of effort. Here is a snapshot of my assembler code. As you can see, I'm using classic design patterns such as factory, command, and listener to follow the design principles of separation of concerns, abstraction, and divide and conquer. On the right-hand side, you can see the assembler code for parsing SLL and SRL instructions. Here are the 3 special features of my assembler. I am using .equ as a memory address assignment operator for the assembler. I am also using $sign as a variable with the current memory address location. I am using .ascii directive for storing an ASCII string in memory. Next, I wrote a Java-based emulator to simulate the CPU. This includes the data path, memory, control, and input-output. It was very useful for testing the instruction set and the assembler. I added disassembler as a special features of the assembler and the emulator. Next, I started designing the sequencer. I wanted to have a simple sequencer finite state machine, and I also wanted to have separation of I/O and sequencer concerns. Therefore, I created a sequencer finite state machine which uses I/O controller finite state machine via a handshake. Here is the state diagram of sequencer finite state machine. As you can see, when the sequencer starts up, the program counter is set to 0 in the start state and instruction. And it moves to the next state for reading the instruction from memory. Once the instruction is read from memory, the instruction is loaded into IR. I also added a special feature for pausing or resuming the instruction execution. If the computer is not paused, it moves to the execute instruction state, and from there, it writes the result, computes the program counter, and continues to the next instruction. If the computer is paused, it waits on the pause state until it is asked for, until it is unpaused. For simplicity, I stick to rising edge clocking scheme with 6 clock 1. As I was designing the sequencer, I also updated the steps for executing each instruction. For example, here are the steps for LUI and SLL instructions. Both of these instructions use the barrel shifter. LUI instruction uses a fixed shift amount of 8 bits with shift left direction, whereas the SLL and SRL instructions have variable shift amount up to 15 bits. Next, I wrote VHDL for sequencer finite state machine and the entire computer. I found that by separating the sequential versus combinational logic and by abstracting the 7-segment display rendering, sequencer and I/O control FSM, their handshakes, I was able to write well-organized VHDL code. I used divide and conquer principle for writing the barrel shifter and the ALU. So let's move on to a quick demo to see how it all came together. For the demo, I'm using the multiplication program with a range check for 16-bit input numbers. The range check program looks at the given 16-bit number and returns 1 if and only if the given number is out of the range. The program also echoes the inputted values. For the demo, I'm using the multiplication program with a range check for 16-bit input numbers. Let's try a happy use case. Let's multiply 7 by 3. Cool, the result is 21 as expected. Let's try an edge case. Multiply 32,768. Okay, as you can see, this number is out of range, so we correctly get an error. Now let's try 32,767. Now multiply this by 1. Cool, that works. Now let's try another edge case, negative 32,769. So we correctly get integer out of range error again. Now we can try a few more numbers. Example, demonstrate one of the shortcomings of this program. Let's try 4,000 with 50. So the result is going to be more than 16 bits, and therefore it will overflow. You can try a few other examples, such as 0.2 multiply by 2. Result is correct, 4. Let's try to multiply two negative numbers. So minus 2 multiplied by minus 6. Now let's try invalid decimal number. So I'm treating invalid numbers as 0. So let's multiply this with 3. The result should be 0. Alright, cool. So that's basically it for the demo. I also added following debugging features. I am outputting the comments and the disassemble instructions to the memory initialization file. I can see the ALU inputs and the output using the slide switches. I can also use the slide switches to see the register values, and I'm using LEDs to show the state of memory and sequencer finite state machines. I have slide switches for clock hold, clock stop, and memory suspend. I have a push button for computer restarts, and also a slide switch for pausing the computer instruction, and a push button for resuming the instruction. So that's basically all I had for the presentation. Thank you so much. I hope you enjoyed it.